Howdy and welcome back. So in the previous video, we talked about binary trees, the idea that nodes presenting within our binary tree would have at most two number of children. The question becomes, what if we want to create a tree whose, nodes have, a greater number of children than just two? If we think about wanting to design maybe a node that has, I don't know, k number of children, uh, how would we store, each of those pointers? It doesn't make a lot of sense to have like child one equals some address, child two equals some address. Well, what we could do is go ahead and structure a node like this. Here, let me draw this out quick. So I don't know, maybe, something like this, unbound tree, single pointer up to the parent of this particular node, and then some sort of array holding k number of pointers to objects of node type, name children to house the pointers to the children, and then data. As you'll learn in your algorithms class, if we wanted to have, say, node containing some arbitrary number of children, there's some complexities involved with this, especially when it comes down to the allocation of, say, some sort of array to store those pointers in. So, and again, don't spend too much time on this. I'm not going to have any sort of test questions on this video, but do, watch through it to see some of the implications of this. So this is one approach, and here's the better approach, which the Introduction to Algorithms textbook, I think, sets up very well, and you'll likely encounter this in 225, and if not, there's a reference for you right down at the bottom where this diagram came from. But the idea here is going to be to kind of create this illusion of an arbitrary number of children for a specific node, and how this is going to be implemented is going to be within the actual node structure. So instead of containing some sort of arrays of pointers to, say, a node, all of a node's children, instead we're going to set up a node to simply have a pointer to its parent, a pointer to its left child, and then a pointer to its right sibling. And we'll see that through lateral movement, so through the right sibling pointer, we're going to effectively provide a node with a node and ability to have an arbitrary number of children. And of course, these nodes will also store some sort of data T. So if we go ahead and look at our root here, the question is, how many children does that root have? Well, we can only access the left child, so we can move down to here. Okay, cool. So how do we access the rest of the children that belong to the root? Well, we simply follow these sibling pointers to hop over, and we can access the next child of root. And if you actually look at this, it's almost like a linked list of siblings, with the caveat that each of those kind of afford the opportunity to take a branch down to visit to visit its kind of collection of children. But anyways, just following these, we can see that, okay, in this case, root has 3 children. How do we know when we're at the last child of root? Well, after traversing the right sibling pointer, will eventually arrive at one that points to the null pointer. Whoa, this almost looks like, a singly linked list, and that, okay, move, 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 and each element within that right sibling direction is going to be a child of the root. And the cool thing here too is each of these children point back to their parents. So there is super easy access if you need to get back to the parent node. Yeah, it is a bit more difficult to move back to the previous child, and you do have to run through this list of, say, visiting each of the children to kind of access the next children, but it will prove a bit more effective in terms of both performance and space than what this representation does up here. And again, I'm going to defer that discussion to 225, but I'm just pointing out, here's kind of one implementation. If you want some sort of node, so in this case, we're focusing on root, to have an arbitrary number of children. And we can just see this by, say, looking at root's left child's children. In this case, we see 2. I'll go ahead and put this in a bit of a different color, kind of internal to that. So its children, it only has 2. if you look at, say, this particular child of root over here, it has 4 children. So look at this arbitrary number of children that a particular node can now have. Pretty interesting. And this is kind of a, cool implementation. And again, it will have performance implications that makes structuring things in this manner a bit more effective than doing it in that when we're talking about each number of node having a different number of children. So again, this is each node has an arbitrary number of children. So it can be, it's not like between 0 and k, it's k is kind of dependent on the specific node and it could change. You could easily, just looking at this, if we wanted an additional node here, let me just try and draw this out. Let me pause, draw it quick. So you could easily tag in, say, another child to the root node shown here in orange. And think about this. I mean, if these were all stored as pointers to an array, what are the implications of that? You remember kind of the resize process. Now, if each node had a fixed number of children, maybe the array would be a better trade-off. But if you have this arbitrary nature, arbitrary number of children, is it easier to, I don't know, grow our linked list here or grow in an array and leave potentially unused space? What are the memory implications of that? So, just sit down and kind of think about these trade-offs because they are interesting and you'll really get into them in 225. And I, obviously don't want to tread on them here. So it's just, here's a tree with unbounded branching. It could have 2 children, 1 children, no children, effectively an infinite number of children as long as, it fits within the constraints of the memory allocated to your program. And again, contrast this if we did have this fixed number of children, if it was always between 0 and k, maybe this approach might be better in that particular instance versus, again, this unbounded branching instance here. So with that, we're going to have one more brief section today, and then we will get into our binary search trees tomorrow. So one more video to go, and then we're done.